Okay, hi everyone. Thanks for joining us today. We are very excited to talk about foundations of data-efficient learning, which is becoming more and more important with all the large data sets and large models that we are doing machine learning with today. Okay, so we are going to talk about, thanks. Okay. Okay, thanks. So we are going to have 3 parts in our tutorial today. So between part 1 and 2, we are going to have more or less 10 minutes break. Part 1, we are planning to have between 40 to 45 minutes, 10 minutes break. Part 2, around 20 to 85 minutes, 10 minutes break, and 30 minutes for the last part. So please feel free to interrupt us and ask questions during the presentation if you wish. So we will answer the quick ones, and if there are longer questions, we are very happy to take offline. Okay, so let's start with the motivation. Why do we care about data-efficient learning? Okay, so as you know, data is the fuel for our machine learning tasks. And this is not a new conclusion. We knew this for the last couple of years now. Here's an example of object detection from Google AI from 2017. Like almost 7 years old now. And if you look at the x-axis, you see the number of examples. As we increase the number of examples from 10 million all the way up to 300 million, you see the performance of this object detection on the y-axis in log scale. And you get this logarithmic improvement in the performance of object detection tasks. So clearly, this shows and confirms the importance of data. However, if we look at the way that we have improved the accuracy of our machine learning tasks over the past couple of years, so here I'm showing you the model size in billions of parameters, and x-axis is years. So orange shows the size of the vision models from 2012 all the way up to 2023. Orange shows the blue shows the size of language models. And you see that mainly the way that we improve the performance of these models is by increasing their size in terms of the number of parameters that they have. So in particular, we increased massively. We went in 2021 to trillions of parameters for our models. And we came up like in this paper, which is from OpenAI, if I'm not mistaken. There was a scaling law effect that was observed that by increasing the model size, we can increase the performance. Now, if you look at what happens after 2021, since this paper is published, you see that suddenly, in particular for these huge language models, we went down with the size. We went to smaller with the size of the models. And what happens was that there was another paper from DeepMind in 2022 that says that if we want to get the optimal performance, and if we increase the size of our model by twice as large, we should also increase the data size proportionally twice as much. Otherwise, our machine learning models are going to be undertrained, and we are not getting the optimal performance. So this was kind of a little bit contradictory to the previous scaling law effect that was observed. And now, people went down with the size of the models, and we started to increasing massively the size of our training data sets since then. So if you look at these 2 plots, again, left is for language models, training language models data size, and right is for training vision models over years. You see that the last couple of years, we went huge. Like, again, y-axis is log scale, so a small difference in the end is a huge difference in the size of the training data. We went to, again, trillions of tokens and for language models and billions of examples for vision models. We scaled our training data massively. And this helps. But these huge data sets, like training these models and these huge data sets, so this is there is a lot of issues with sustainability and also safety of these machine learning models. Like this huge amount of data it's very hard to make sure that the model that we train, we can trust it, and all these data points are kind of high quality. There is nothing kind of bad in them, such that they affect the performance of our models negatively. Okay, so let's go over the problems one by one. So first of all, very, very expensive training these large models on these large data sets. So if you look at the training cost in terms of dollars, from 2017 to 2023, you see that now, in 2023, we are training models that are 100 million or 200 millions of dollars, and these costs that are estimated, they are usually one-time training. And you know that to get a very good quality model, we usually train multiple times, right? So this is just one-time estimate of the cost of training these models. And some sources estimate that by 2025, we may train models that cost up to $10 billion. Hopefully, not the right estimation, and we can do better, but the way we are doing is just cost is very, very expensive. Okay, even if we are okay with the costs, there is another issue. So here you see the amount of CO2 that we are producing by training these huge models. So here you see like how much CO2 produces by traveling per person from New York to San Francisco, or what is the produced CO2 by human during their life. Then how much does a car in the US produces CO2 over its entire usage and lifetime. And then training AI models in 2019 cost 800, this is Ks of CO2, and now look at 2024. Huge, right? For estimate, again, like these numbers are not reported, but they are estimated to be between 400K and 700K tons of CO2, not kilos, tons, right? So this affects very much negatively the climate. Okay. So what is another issue? Another issue, like instead of putting as an issue, I put it in the positive language. A lot of times, by going smaller with the size of the data, but improving their quality, like if we can find a smaller, higher quality subsets of the same large training data, we can improve the performance, right? And this is very, very useful. And there are two ways we can do this. One is data filtering methods. That are methods that are filtering noisy examples, duplicate examples, or irrelevant data, most of the times heuristic methods. For example, I show you two examples. One is CLIP, training the multimodal vision language models. If you look at, for example, some results from Datacom, you see that if we train CLIP on 12.8 billion of examples, image caption pairs, we get this accuracy, which is around 62 on ImageNet, classification accuracy, zero shot. But now, if we filter this data from almost 30 billion to 1.5, we are getting even slightly better accuracy, right? So this is a subset of that very big data. Now let's look at, this is like almost 90% reduction that we can improve the performance with. Now let's look at training language models. This is recent Datacom language model results. So you see that again, if we improve the quality of the data, we can go 40% less with the amount of data that we train, and we can improve the performance by almost 6.6%. So this is again log scale on the x-axis, so this is small arrow translates to a lot. Okay. Another way is data selection. Consider that, imagine that we have a filtered data. There is no bad data or irrelevant data in it. Still, there is going to be a lot of redundancy in these huge data sets. So again, I'm showing you two examples from CLIP and language models. Starting with CLIP, this is training on conceptual caption 3 million examples, which is, doesn't contain noisy and bad stuff. So now 3 million examples, we get this accuracy on ImageNet. We can reduce the size of data by a half just by dropping the redundancies. And we can do the same, or sometimes slightly better. Let's look at language model fine-tuning. This is fine-tuning via on the math instruct dataset for solving mathematics questions. Now you see that if we go, if we go with 11% of this data only, here you see 90% reduction in the size. The dashed black line is the full data performance. We can already outperform it. And now, if we keep kind of increasing the size of the data, but non-redundant examples we select, when we get to 38%, we are outperforming full data by a lot, right? So this is another thing that we have to be careful about. Other problems, I go over this very quickly, just that you know about these problems. So a lot of times, these huge data sets that we train on, they are very imbalanced, not only in terms of class imbalance, but also feature imbalance. And what happens is that, for example, imagine this is an example of a self-driving data. Majority of this data belongs to the cars and pedestrians and traffic signs. Only a minority are this very important class of accidents and crashes. This is a real example of an Uber accident who killed somebody. If we just train on this huge data as they are, we are going to miss this very small kind of group in the data, and we cannot ensure safety. And this also causes this imbalance, feature imbalance, and class imbalance causes other issues, fairness and safety. And a lot of times, OOD, we cannot have a good out-of-distribution performance when we have a slight distribution shift between training and deployment data. Another problem, real data sets that we usually crawl from the internet, these large ones, they are usually unlabeled. And if we want to do supervised learning, we usually need to label them ourselves. We usually do crowdsourcing or automated labeling. We introduce a lot of noisy examples, and they drop the performance. Last issue, many of these large data sets, they are from, we crawl them from user-provided sources. And a lot of times, people can insert malicious examples. Like a few malicious examples people can insert. We train the model, everything goes well, performance is good. In the test time, the target example that the adversary likes is going to be misclassified to the class that adversary likes. And because these examples, these attacks, like the targeted data poisoning attacks or different kind of attacks in general, are very difficult to capture, to detect, because nothing is going wrong during the training. But you may let a bad person in your system, and these are actually very kind of hard to detect. Okay. So the big question is that, can we select the smaller subsets of large data sets to improve efficiency, performance, and robustness of learning from large data sets? So today, we want to focus on efficiency and performance and sustainability of training these big models. But many of the things that I talk about, they also have applications to ensure robustness of our models. I mentioned some very briefly. Okay. So first question, why can we even expect to do better with the smaller data compared to large data? We know that the more data, the better, right? So the key insight is that as we increase the size of our data sets, there is going to be like the amount of information in these large data sets is not increasing linearly. It's kind of, there's a diminishing returns. Because of all this redundancy that we get in these huge data sets, the amount of information increases kind of in a concave way. And if we can reduce or eliminate all these redundancies and kind of find this the smallest, most informative, like all the information with a smaller amount of data, which let's call it information volume, then by training the model on this smaller, more informative or most informative subsets, then the model can learn the information much better, right? This is kind of a high-level idea. Okay, so there is a hope. And as I mentioned, there are two ways we do this. Data filtering methods that they can capture and drop the obvious mistakes, but they cannot usually eliminate redundancies. Second approach is that we define an optimization problem. We find the smaller subsets that we can ensure if we train on them, we get the same generalization performance or better generalization performance than training on the full big data. And a lot of times, we can also get a curriculum, theoretically, of what is most important to be trained on at which times during the training. Okay, so this is what we want to talk about today. Okay, so how can we find this kind of subsets, the most informative subsets, most beneficial subsets? So let's formalize our problem. So we want to find this S star, a smallest subset, that maximizes a set function. This set function tells us how good each subset of the big data is for training. Like if we find on this subset, what is the performance that we expect? Subject to sub-budget constraint or cardinality constraint. So the big question is that what should be this set function? What should be f? And to be concrete, like imagine we have a big data on the left. We want to find this smallest subset on the right, such that if we train a model on the left and on the right, we get more or less the same model or a similar performance. If we can do this, we can speed up our training by size of the big data B over the size of the small data on the right, which is S. Okay. So how can we think about finding such a subset? So first of all, like let's think a little bit about it together. One way is that maybe we should choose the data points around the boundary, such that the model can get the boundaries correctly. Another way is that, or maybe we should select a diverse subset such that we get an idea of how our data is distributed. Not super clear which one is best. So we should be able to find it quickly, such that we train on it and we get the speed up. And we also want to have some theoretical guarantees that if we train on this subset, we will get a good performance. Okay. So this was the motivation problem formulation. Let's start with data-efficient supervised learning. Okay. So how do we do supervised learning? We have a big data of features X and labels Y, Xi and Yi. And the way we train is that we define a loss function per example, and then we also usually have a regularizer, and we take a sum of all of these loss functions plus our regularizer. We call this our global loss function. We try to minimize it to find W star, the parameters of the model that minimizes this loss function over all the examples in our data. This is the standard formulation we use to train convex models like linear and logistic regression, SVMs, and non-convex models, for example, neural networks. Similar formulation. So now, how do we minimize this loss function? We usually do some sort of gradient descent, right? For example, we take one example or a subset of examples at random. We make a move in the negative direction of their gradients, and we minimize the loss. We keep doing this until the loss is minimized. This is usually very slow on large data sets. It converges to some global or local optimum, but it's very slow. Okay, now let's, with this kind of have in mind, what should be this subset that can guarantee the performance for us? No matter what the model is, we know that we want to do gradient descent, right, to minimize the loss. So the idea is that if we can find a subset that has a similar gradient to the gradient of the full data during the training, now we can do gradient descent on the subset, and we minimize a similar loss, and the parameters change the same way as if we train on the full data, right? So technically, we want to minimize the difference between the gradient of the subset and assume that we can also weight the examples in the subset too. Minimize the difference between the weighted gradient of the subset and the gradient of the full data. And we can tolerate an epsilon error. During the training, we want this to hold. Okay, how can we find such a subset? Without going into the steps, there are a couple of steps. Let me show you the solution. And the solution is intuitively simple. I'm hoping that you can believe me. So this is our big training data. For a second, imagine that we can transfer all this data, which is in the feature space, to the gradient space. We can calculate the gradient for all these examples. Now I have all the gradients. Imagine that I can cluster them. Now I can take the cluster centers of these gradients. I can weight every center by the size of the cluster, the corresponding cluster. And now the size of the weighted cluster centers have a very similar gradient to the gradient of full data. right? Okay. So this is how we can find a subset, but notice that I said for a second, imagine that we calculate the gradients, and the gradients depend on the parameters. Which parameters shall we find a subset for? Now this becomes a question. Okay. So first of all, how can we solve this problem, the clustering problem, in a big data quickly? So this clustering problem is actually is called exemplar clustering, which we can write it in this way. And this is a submodular function. Submodularity is a property of set function. Some set functions have this property, which is a diminishing returns property, which means that if we add a new example to a larger subset, the gain is going to be smaller than if we add the same example to a smaller subset. There is a good tutorial on submodularity in ICML at ICML 2013, which if you want to know more about submodularity, that's a great tutorial. But short message is that if a set function has this property, then we can find the subset by maximizing a submodular function very efficiently, very quickly, using a simple greedy algorithm, if this is a monotone submodular function. So we can find the subset. Even if you don't know submodular function, we can find the subset from big data very quickly. So we are good here. However, for which parameters? Shall we calculate the gradient and then find the subset? We don't want to do this after every SGD step. That's very slow. Okay, so let's look at this submodular objective function. This submodular objective function, what we need to solve it is the pairwise gradient similarity that you see between all the examples, I and j, right? So if we can upper bound these pairwise gradient similarities for all the W, then we can get rid of this dependency to W, right? And we get this new objective function, which is upper bound on the original function. Now we can solve this new objective function, which doesn't depend on W, right? This is using the worst case pairwise difference between gradients for all the W. Okay, let's call this Dij, and our new problem is solving this sum of Dij's to be less than epsilon. How can we find Dij? Okay. Short answer is that if we have a convex function, if you are training regression or SVM, so Dij's can be bounded by a constant times the difference between feature vectors. So even before we start the training, we can cluster all the feature vectors, and we can find the centers of feature vectors. We can weight every feature vector by the size of its cluster, and we can find the subset. We ignore the full data. We train the regression or SVM function only on this subset, and we are done, right? We don't need to be worried about. So this becomes just a pre-processing step. How about neural networks, which we are more excited about these days? We don't have this nice property for neural networks. So what we can do is that instead of calculating the full gradient, which is not useful, so there are some results that are showing that most of the variation in the gradients is captured by the gradient of the loss with respect to the last layer of the neural network, right? For example, if you are training a classification model, we have a softmax cross entropy, and the gradient of the cross entropy with respect to the input to the softmax just becomes the logit vector. So we do a forward pass, we get the logit vectors, we cluster the logit vectors, we take the centers, we train on them, and we move on. But this is, if you notice, this still depends on W. So we have to update this subset during the training, every now and then. And I will talk about when. Okay. So let's quickly look at some experiments. Let's first look at training convex functions. Summarizing the algorithm first, sorry. So we use the greedy algorithm to find all the centers of the gradient space where gradients are approximate gradients. Then we weight every center by the size of its cluster, and we do our favorite gradient method on the weighted cluster centers of the approximate gradients. Meaning that if there's a larger cluster, center of larger cluster, we move more, we have a larger step size, and if we are moving based on the center of a smaller cluster, we move by a smaller amount. And we do this during training, and we are good. And we get the guarantee that we are converging to the near optimal solution, meaning that we can train a very similar model, but much, much faster. Same convergence guarantee on the smaller data translates to much faster. Okay, look at some experiments. This is an example of a very imbalanced data. We are training a logistic regression here. We have 9-to-1 class imbalance ratio. If we are training on random subsets of size 10% all the way to 90%, we cannot get close to this bottom orange point, which is training on full data. But if we use our method, which we call Craig, after finding a 30% subset, we can already match the full data, and we get up to 7% speed up. Another example, let's start with the toy neural network, training MNIST with a 1 hidden layer neural network. This is training on full data. Left is test accuracy, right is training loss, x-axis is time, including the time to find the subset. So this is our method, and this is random subsets. You see that this is doing much better than random subsets and even better than full data. We are good, and we are getting 2 to 3x speed up. Here I'm updating the subset at the beginning of every epoch. Okay. So we are good with convex function, but we don't have any guarantee for neural networks yet. So can we get some sort of a guarantee for neural networks too? Okay. What is the difference? Let's think of what is the difference between the neural network case and the convex case. First difference is that we have a very non-convex landscape when we are training the neural networks. So this is the first challenge. We have to somehow take care of how to deal with non-convexity. We know that whatever guarantee that we have so far is for convex functions, convex loss functions. And I mentioned that we have to update the subset, but when do we need to update the subset such that we get guarantees? The second challenge is that we are usually training deep networks with mini-batch SGD. Otherwise, our training is going to be very slow. You cannot do SGD. Right? We do mini-batch SGD. And now we have to find mini-batches. We cannot go with just one large subsets. We need smaller mini-batches. We need to find the smaller mini-batches during the training such that they can guarantee the performance of mini-batch SGD for us. Okay, let's see how we can address these challenges, these two challenges now. So for the first one, the main question is that when should we update the subset such that we can still guarantee the performance? So the idea here is that, let's say that we are at the beginning of the training, we are at the left-hand side of the blue curve, right? At that point, we can use the global gradient and curvature estimates, right, to do a second-order Taylor approximation to model the loss with a second-order Taylor approximation, technically a quadratic function with the local gradient and Hessian estimate. So we do this, and we find one subset at the beginning of the blue region. Now, because this blue region is convex, we know that this subset is good as long as we are within this blue region, right? So we keep training on this subset, and we have to check. Now, the only thing we need to figure out is that when do we get out of this blue region? So we keep training on this blue region, and I think the solution that I have is in the next slide. Oops, I think this slide is lost. Anyways. So we find one subset at the beginning of the blue region, we keep training on it, and we keep checking the difference between the blue and the original loss, which is the black non-convex loss. Whenever this distance between the blue and the black becomes larger than a threshold, we know that we are out of this convex region, the blue convex region. At that point, we know that we have to update the subset. So what we do is that as soon as this difference between blue and black becomes large, we do another quadratic approximation with the gradient at Hessian at the end of the blue, right? And we update the subset. Then now we know that we can keep training on the subset as long as we are in this new red convex region, right? As soon as we get out of red, we do a green quadratic fitting. We find one subset, and we know that we are good as long as we are within this green quadratic region. Okay, so we are done with the first challenge. Now, let's think of how we can find mini-batch subsets. Whatever I said so far is just one subset from full data. Okay. So what is the idea? Like, why mini-batch SGD works? The idea is that the reason that mini-batch SGD converges faster than SGD is that the variance of mini-batch gradients is smaller than the variance of individual gradients, right? You may know already about this. So the larger the mini-batch is, as long as it's not too large, we can speed up training by the size of that mini-batch because the variance increases proportionally. Okay. Now here, our idea to find mini-batch subsets is that let's take a large random subset, for example, 1,000 example. Let's use our clustering formulation to find a small subset of the mini-batch size that we want, for example, 128, from this 1,000 examples. Now this is a mini-batch subset. Let's take another random subset of size 1,000, for example. We find another 128 mini-batch from it. We can do this 10 times, right? At the beginning of the blue, instead of finding one subset from full data, now we can find 10 mini-batch subsets from 10 larger random subsets. And because these smaller mini-batch subsets closely match the gradient of these larger random subsets, which are larger mini-batches technically, so training on these smaller mini-batch subsets can speed up training very much because they are simulating training on the very large mini-batches. Okay. So we do this at the beginning of blue. We keep comparing the loss. When we get to the red region, we update all these mini-batches. When we get to the green region, we update all these mini-batches. Okay, now this is the final algorithm. And now we can get guarantee for the convergence to stationary point of our non-convex loss, the same one that training on full data converges to. And you see that we have this R in the denominator of the convergence rate. This is the size of the big mini-batch. So we are simulating training with large mini-batch size. And that's where the speed up is coming from. Okay. Let's quickly look at some experiments and move on. So let's imagine that we have a budget of 10% of the full training. For example, training on CFAR10 has 200 epochs, we want to do 10% of that. Or same with the other data sets. So you see that compared to other subset selection methods that select one subset from the full data, if we select mini batches from larger random subsets, now we can do much closer to training on the full data. We get much better accuracies. And it also scales much more because training one subset from full data is very expensive. But training a small subset from a smaller random subset is very, very fast. Right, so it also scales very easily to large data sets. And we also get a speed up. This is, again, the time, including the time to find a subset. Okay, great. So, but let's look at how much we update the subset during the training. If you look at this left plot, top left, this red box, you see that, look at the green line. Early in training, the loss is very non-convex, right? And we keep updating the subset a lot. Then after some point, the updates become less and less and less. This is the cumulative total number of updates. Because the loss becomes flatter and flatter and flatter during the training, now all these flat regions, one subset is good enough for us. We don't need to update. Okay, so we don't update as much later for the green line, which is our method. And so let's also see, like we are getting a curriculum, right? Because we are also updating these subsets during the training. Let's look at what is this curriculum that we got from this algorithm. So x-axis, the bottom plot, is the epochs of training. And y-axis shows the average difficulty, learning difficulty, of examples that are in the subset. So here, we are measuring this in terms of the forgetting score that I will show later in the slides. So forgetting score counts how many times the prediction of an example changes from correct to wrong during the training. As we train, the prediction of example changes. the more prediction of an example changes from correct to wrong, that example is more difficult to learn for the model. The network struggles to learn. Okay. So you see that the average difficulty of the subsets that we find increases during the training. So we start with easier to learn examples, and we keep increasing and increasing the difficulty of examples during the training, and this makes a lot of sense. Like if you want to teach a kid what is a cat, you show the simple cats first, then you increase the difficulty of learning, or difficulty of like vaguer or ambiguous cats, you show them it later. Okay. So similar framework we can use to train our models robust against noisy labels data poisoning attacks. I don't get into this, but I just put a few references here if some of you want to check later. Short message is that the exact same method that I mentioned can theoretically guarantee that we are not selecting a lot of noisy labels during training. For data poisoning, gradient clusters of size 1, if we discard them, we can train robust to data poisoning attacks. We only need to do this early in training. And if we balance these gradient clusters early in training, we can also train robust against the spurious correlations, and we get a much better OD performance. Okay. So far, I talked about all these theoretically rigorous methods, but there are also a lot of heuristics for selecting subsets that generalize similar to training on full data. So I also want to quickly show you some of them. The intuition behind all these heuristics is that let's find the difficult to learn examples in our data set and only train on them. And let's ignore the easy to learn data sets when we do supervised learning. First heuristic metric is forgetting a score. I already explained what is forgetting a score, the number of times that the prediction of an example changes from correct to wrong during the training, right? So difficult to learn examples are more forgettable. And if you look at the top left plot, so red is the performance accuracy of training on the full C410. Blue is training on random subsets. Size is on the x-axis. From big to small, we discard randomly examples. That is the blue line performance. And if you keep the most forgettable examples and you discard the least forgettable examples, for example, the network learns them, never forgets them during the training, you can almost discard 30% of your data without losing the accuracy at all. Right. So keep the difficult, discard the easy, we are going to be good. The only issue is that we have to train the network first. To calculate these forgetting scores, now we have to restart, and now we can get efficiency, data efficiency. Okay, another issue is that forgetting scores is larger usually for the noisy labeled examples. Intuitively, this makes sense. So if we do the forgetting score, and if there are noisy labels in the data, we are going to be affected by that. We are going to select them too. Another metric is called LTune. The way it works is that we train 10 models, the same models, from 10 different initializations. Each of them we train only for 20 epochs. Right, I'm talking about training ResNet on C410. Now, after 20 epochs, we have 10 models. We calculate the average gradient norm of different examples. And when I say gradient norm, you can think of the gradient that I was using, the last layer gradient, the logits, norm of the logits, right? Expected norm of the logits, we calculate for all the examples over these 10 different training runs. We choose the examples with largest gradient norm, expected gradient norm. Okay, this is also working. This is the blue line, and forgetting the score is the orange line. You can see that they are similar, and we can discard a lot of examples by keeping the more difficult examples and without losing the accuracy. LTune is also affected by label noise, meaning that if we have noisy labels, we are going to select them, and that affects the performance. Okay, last one. So this is classification for language data sets. I'm talking about supervised learning, so classification, not generative models yet. So this paper says that if we calculate the variance of the true class probability for every example during the training, the examples with a lot of variance, those are difficult to learn. So high confidence, low variance, these are the easy ones. We don't want them. We can discard. Low confidence, low variance, these are the noisy labeled examples, a lot of them. So we also don't want them. So let's stick to this middle range, right? Let's only keep them. And this doesn't include easy examples. This doesn't include noisy labeled examples, right? So this generalizes best. Of course, there is a threshold that should be tuned. Okay. So now, another paper shows that most of these heuristics on the diagram, these are correlated with each other. Left heat map shows the correlation of examples selected by different heuristics. But important is the right plot. The right plot shows that if we discard a lot of examples, if we discard 60% of our data with all of these heuristics, no matter which one, none of them can give us a good subset. Now you can think of why. We keep all the difficult examples. We discard 60% of our data. We remain with all these outliers and noisy examples, and there is nothing in our data that is good enough. So with these heuristics, we cannot discard a lot. They are working well as long as we want to discard a small amount. Okay. So this is the short message. So if we want to do heuristics, if we want to find a very small subset of examples, we should keep the easy ones. But if we want to remain with a larger subset, we should find the difficult ones. And all of these heuristics are finding the difficult ones, and they work. Let's contrast this with the theoretically motivated approach that I was talking about in the beginning. So one difference is that none of these heuristics can take into account the redundancy. Like if two examples are similar, we may not need both, but they will have a similar forgetting score, and they will have a similar L2 score, and all that. So they will either select both or none, right? So they cannot get rid of redundancies. Now this plot may make more sense, right? If you are interested in finding a very small subset out of a big data, we are going to only find the easy ones with our theoretical approach, and we will do well. Now, if we want to do larger, if our budget is larger, over the time, we keep focusing and selecting the difficult examples over and over, right? So we are also doing fine. But this is the intuition behind why heuristics work, right? So if the difficult example subset is large enough, they will contain enough of easy examples. So they preserve the gradient kind of during the training. But if we use our theoretical approach, this will be taken care of. We don't need to be worried about the size of the subset. And we get theoretical guarantees. Okay, so another interesting thing is that you see the point that the blue line starts, that is for getting a score average of 6. So we are never selecting the very easy examples, even with this theoretical approach that I introduced. So we don't usually need the very easy examples. We start with easy, but not easiest, and then we increase the difficulty, and we can do best. Okay, let's take a 10-minute break roughly, and Sid is going to talk about data-efficient self-supervised learning. We are happy to take questions in the meantime. Thank you.
Yeah. So now that Baharan has explained the principles of data-efficient supervised learning, we can now think about exploring this for self-supervised learning. And that's this part of the talk now. So we've established how careful data selection can make training deep networks with supervised learning much more efficient. However, supervised learning requires high-quality labels, and getting these high-quality labels is extremely expensive. And also, if we have mislabeled examples, this can drastically affect our performance. So how do we then train with these massive data sets that we have today, but without labels? So the obvious answer is we can do pre-training with self-supervision, which is we can exploit the supervision that the data provides and learn from it without labels. So the benefits of pre-training are, of course, we don't need labels, right? Like that's the main benefit. But also, you can quickly adapt models that are pre-trained with self-supervised learning to new tasks. And also, you can get much better robustness to distribution shift. And for example, we can think of a method like contrastive learning as like one of the best performing self-supervised learning pre-training methods. And here, essentially, you learn through the self-supervision provided by the augmentations of a large pool of images or text data. And here you can think of methods like SimCLR, etc. No worries if you're not familiar with contrastive learning, because I'm going to describe it now in the next slides. Cool. So the way self-supervised contrastive learning works is that our goal is to learn an image encoder. And we do so by pulling augmentations from the same example closer together. And that's what the numerator does. And pushing augmentations from different examples further away. And that's what the denominator does. And the way we use these models is there's like a two-step process. The first step, as I described, was the pre-training with the loss function I showed in the last slide. Once we pre-train with contrastive learning, we get some representations for our data. And then we train a linear model on these representations with some small fraction of labels that we do have. So earlier, we used to need all the labels for supervised learning, but now we can just use a small fraction and train a simple linear model on the representations that we got from contrastive learning. And this method is called the linear probe, and this is how we evaluate how good the representations learned by contrastive learning are. So, however, while contrastive learning has all these benefits, it has no label requirements, faster adaptation to new tasks, and better robustness to distribution shift, it comes at a huge cost. Here I have like a sample plot showing the cost of training a model that gets equivalent performance on ImageNet using supervised learning and contrastive learning. And approximately, contrastive learning is at least 10 times more expensive, if not more, because one, contrastive learning converges slower, and two, the computation of the loss function, etc., is also slower. So you can kind of guess where this is going, right? Our idea is, can we improve this cost problem of SSL pre-training by focusing on data efficiency? In that, can we select subsets for SSL pre-training that have the same performance as training on the full data? Okay, so from our understanding of data-efficient supervised learning, our first guess is going to be, can we match gradients? That is, can we select a subset such that the gradient of the subset matches the gradient of the full data? However, as you can see in this loss function here, the loss and gradient of every example depends on all the other examples. If you look at the denominator there, there's an iteration over all the other examples in a batch. And so we can't really isolate what the loss or gradient for a single example is in this case. And then similarly, for other metrics like forgetting score, L-tune, etc., the same problems exist. Like we're not able to identify what the hardness or forgetting score of a single point is in this setting. And so gradient matching is kind of out of the picture now. So then let's go back to the drawing board. And we'll start by going under the hood and understanding better how exactly contrastive learning works. So the way contrastive learning works, we can say it achieves sort of two properties, and let's call these alignment and divergence. So the first property, which is alignment, simply refers to the fact that after you've done contrastive learning, the representations of augmentations of the same example are going to be very close together. So here I have a little animation for that. And the second idea is divergence, right? And let's understand this step by step. So we can think of every latent class as having some center, like the average representation of that latent class. Here I've shown the average representation of the cat class. And what divergence means is that we're saying that contrastive learning ensures that these average representations of the latent classes will be well separated. So in summary, what contrastive learning is doing for us is that it's clustering these augmentations of the same example and separating centers of different latent classes. And hence, you kind of have this nice property of like a clustering and representation space happening. And that kind of gives us a starting point, right? Because now we can break down our problem into trying to find a core set or a subset that preserves alignment and divergence of the full data. We're no longer trying to like just directly match contrastive learning performance. We can break it down into these two terms. And if we can do so, we can effectively match the gradients. So like the same guarantees we had in the supervised learning case, we can recover them just by matching alignment and divergence. And then, of course, we can guarantee that the performance of training on the subset is going to be similar to the performance of training on the full data. Okay, so I'll take a quick aside to introduce like a useful helper notion, and we'll use this in a couple of slides from now. So since the contrastive loss pushes and pulls examples, the representations of examples based on their similarity, we'll first define this notion of similarity, and let's call it expected augmentation distance. So what expected augmentation distance is, it measures how far apart the augmented views of two samples are. So in the first case, since the augmented views, like the faces and the paws of the two puppies are like very similar, you can say that this is low expected augmentation distance. And in the second case, because these are dissimilar, we'd say this is high expected augmentation distance. And we have the exact expression for it down there, Dij. Okay, so going back to our data efficient contrastive learning approach, right? So we wanted to preserve alignment and divergence. And now we've introduced this notion of expected augmentation distance. So let's start with alignment. How can we preserve the alignment of augmentations? So the key idea is, for every example that we discard, if we can ensure that there is an example in our selected subset with similar augmentations, then we can guarantee the alignment of the discarded example as well. And formally, what this kind of translates to is this expression. Let me break it down here. So here, let's say VK is all the examples in the full data that correspond to class K. Let's call this class dog. SK is the examples we select from latent class dog. And so what we're saying is, for every example that we do not select from latent class dog, there exists some example in our selected subset that has very, very similar augmentations. And why does this work, right? So let's say here we select the green example and we don't select the red example. And these are augmentations of the example that we would select. So when we train on the selected example, we'll bring the representations of the selected example augmentations closer together. But because these augmentations are similar to that of the discarded example as well, we automatically bring them closer as well. And so in this way, by training on only the selected example, we've ensured alignment even for the discarded example. And intuitively, what this is doing is this is selecting a diverse set of examples in every latent class. And I know I'm mentioning latent class again and again, but I'll clarify what I mean by that in a second. And the full derivation for this appears in our paper linked below. Okay, so the next part is, how can we preserve the divergence of class centers? And if you remember, this is the separation of the average representations of different latent classes. So here, the idea is very simple. If we can find a subset that preserves the centers of latent classes, in that the centers of latent classes in the subset are very close to those of the full data, then we kind of automatically have this, right? Because we could separate the full data class centers. And here we bound the distance between the full data class center, latent class center, and the subset latent class center using, again, expected augmentation distance, dij. And the intuition here is that you want to select examples that are central in every latent class. Again, the full derivation appears in the paper. So putting things together now, examples that contribute the most to contrastive learning are those that preserve alignment, which helps us select diverse subsets from every latent class, and those that preserve divergence, which is selecting central examples from every latent class. And there's a little visualization to show like what this might look like. And I'd shown you two objectives for each of these things, and we kind of like relaxed them into this combined objective where we're trying to minimize the sum of expected augmentation distances from the selected examples to the unselected examples. And you can kind of intuitively see why this will ensure both things. Like we're going to preserve the center, and we're also making sure that we always have examples that are similar in our selected set to our unselected set in terms of expected augmentation distance. And yeah, dij again is the expected augmentation distance. And again, we have the property that this set function, like this is again like some sort of set function, and we know that this is also submodular, like we prove in our paper. So again, the same benefits of submodularity come into play. So that was the main algorithm, and we call this algorithm subsets that preserve augmentation similarity, SAS. But there were two kind of key practical details that I left out in my explanation so far. First, how do we compute this expected augmentation distance, right? I told you examples that have similar augmentations, but how do you do that? In pixel space, it's going to be impossible to compute this, and also just because you're taking this expectation over all possible augmentations, it's just not possible to do this. But actually, we can use a cheap proxy model to estimate this. So what I mean by that is a much smaller or partially trained model. So in our paper, we kind of show that to train a ResNet 50 with contrastive learning, you can use a model as small as a ResNet 9 or a ResNet 50 trained for like a couple of epochs to do this. And then the second thing was I kept mentioning latent classes, but that doesn't fully make sense because we don't have labels here, right? So what's up with that? And the way we can solve this problem is, again, we can use the cheap proxy model and do k-means clustering on the representations we get from that. Or we can do the linear probe strategy I described earlier with a small fraction of labels. Or if you don't have these methods available, you can even guess the latent classes using foundational models like CLIP. In our paper, we show that like all of these low-cost methods of estimating latent classes are just as effective. So wrapping up, our intuition is that we want to select examples for contrastive learning that are in some sense representative of all the subclasses in a latent class. So it's like diverse, but also preserving the center. And theoretically, what we show that this does is that it aligns all the examples in the latent class. It preserves the centers of latent classes. And we guarantee generalization of the full data as a consequence of this. So this is an informal sketch of the theorem we have in our paper. And here we're trying to show the error of the linear probe trained on the representations we got by training on the subset, right? And here sigma is a data-dependent constant. R epsilon is another data-dependent constant. And then nu r is this like extra sort of error term we accumulate because we're clearly not preserving the alignment and divergence perfectly. So that's sort of the error of the subset selection part. Okay, so that was the intuition and the theory, etc. Diving into some experiments now. We test this algorithm on a bunch of image classification data sets. And here we can see that for CFAR 100, you can select 80% of the subset and get the same performance as the full data. For STL10, you can go as small as 60%. And for tiny ImageNet as well. And so you can discard up to 40% of examples using this and match the performance of training on the full data. And interestingly, we also find that sometimes this method can even improve performance over training on the full data. So this is for another contrastive learning algorithm called BYOL, and we show that here it can actually improve performance over training on the full data. To sort of sum up, let's kind of get a little bit more intuition about what kinds of examples are we choosing for contrastive learning. So the examples we pick are easy to learn, and these are the ones that contribute the most to contrastive learning. So we can think of them as these like central examples in each subclass of the data. In contrast, the easy-to-learn examples, if you remember from the previous part of this tutorial, they can be excluded usually without harming supervised learning, right? So usually for supervised learning, we like to pick these hard examples that are like near the boundary. And here I have some plots confirming that this is indeed the case. So we show that our algorithm selects the subsets selected by our algorithm are actually very similar to the subsets selected by like the easiest examples. And least forgettable here refers to that. And again, I show here that like the examples deemed worst by our algorithm are actually these hard examples that are the most forgettable and the most useful for supervised learning. So there's this sort of like dichotomy between what's good for supervised learning and what's good for contrastive learning or self-supervised learning. And here I have a little visualization to help us understand like why we don't want to pick boundary points when we're doing some sort of self-supervised learning algorithm, right? So the way we learn with contrastive learning is like we'll do some augmentations. So you can think of that as like moving the point here and there in data space. And if we did that, and the augmentations of these examples that are on the boundary, they would be similar to augmentations of examples from different classes, right? The blue would be similar to augmentations of red, etc. And that would kind of, in the end, result in representations that merge all the classes. And here I have a little examples from what our algorithm selects on CFAR 10 or 100. And here we can see that the selected examples are sort of like, for the bicycle class, are these canonical, very simple representative examples. And the unselected examples are these harder examples that are not as canonical and you could imagine would be on the boundary between classes. And to sum up, we kind of show that like using these ideas, you can speed up training contrastive learning by 40%. Cool. So let's take another 5 to 10 minute break. And then we'll dive into the last part of our presentation that talks about data efficient training of foundational models. Yeah, thank you. Okay, so we've now discussed how we can do data efficient supervised learning. We also then discussed how we can do data efficient self-supervised learning. But today what we work with are these like massive scale foundational models, so to say. And this part of our talk is now going to go into how we can do data efficient training for these foundation models. And the first subpart of this is going to be data efficient contrastive language image pre-training or data efficient CLIP. And let's get started with that. So CLIP learns image and text encoders by pulling representations of image caption pairs closer together and pushing representations of unpaired image captions further away. So the idea of CLIP, I guess I didn't start with this, is that instead of using even augmentations, can we just take paired image caption data that we have on the internet and learn a good image encoder from that? And the way we'll do this is by like pulling representations of paired image captions closer together and pushing representations of unpaired image captions further away. And sort of the great benefit of this is that we can now enable zero-shot transfer of the model to downstream tasks. And what I mean by that is, in CLIP, because we now have trained both a text encoder and an image encoder, what we can do is we can take the classes we care about, let's say plane, cat, dog, bird, etc., and get text embeddings corresponding to these sort of text, corresponding to these classes. and that's T1 through Tn here. And then we can take an image that we want to classify at test time, pass it through our image encoder, and we will know which class this image belongs to by seeing which text representation is it having highest cosine similarity with. So here, since we have a photo of a dog, we can see that the image representation of the dog has highest similarity with the text representation of the caption, a photo of a dog. And you can kind of see why this is very useful. In contrastive learning, while we didn't need labels per se, we still need a small fraction to be able to train our linear model. But here, we don't even need that. And we can generalize in a zero-shot manner to a variety of tasks. So as I just mentioned, the benefits of CLIP pre-training on large datasets is zero-shot classification, even better robustness to distribution shift, but this comes at a cost. CLIP requires a lot more data. So going back to the plot we had earlier, again, we're trying to see like what is the cost of training an equivalent model with different learning algorithms. And we had that contrastive learning is 10 times more expensive. But actually, CLIP, multimodal contrastive learning, can be up to 400 times more expensive. And this is just because of like the large volume of data you need to be able to train a good image and text encoder that can generalize zero-shot to a bunch of different tasks. So again, our focus will be on finding a core set that guarantees similar zero-shot performance to training on the full data. So can we select a subset that preserves performance of the full data? And let's get into it now. So this is the CLIP loss function. I know it looks a little confusing, so I'll also show the visual depiction we had earlier. Let's take a second and try to guess why might gradient matching not work here? So as is probably obvious to you guys by now, since here, again, like contrastive learning, the loss and gradient of every example depends on every other example, you can't rely on gradients to identify like how important a given example is. Same problems as contrastive learning. So again, let's kind of follow the same pattern as before. We can't do gradients, but we kind of want to ensure that the subset we select matches the gradients. And so let's dive a little deeper into how the algorithm works underneath the hood. So prior work has shown that the cross-covariance of data determines the learning dynamics of CLIP. And this is the formal expression for cross-covariance of data, with mu v being the average vision example and mu l being the average text example. But in simple words, what we mean is cross-covariance essentially refers to how keywords in the caption correlate with objects in the image. And more often a keyword appears with a given object, the stronger the correlation will be, and vice versa. So here we can see that our image is a beagle sitting on a couch, and the keywords are beagle and couch, and this may appear like very often, but perhaps beagle with the beagle image will appear even more often, and so there'll be a stronger correlation there. So that's sort of the intuition of what cross-covariance is. And now we can follow the same formula as before. So we couldn't do gradient matching, but we've broken down our problem into this cross-covariance. So now all that remains is that can we find a subset that preserves the cross-covariance of the full data? Cool. So cross-covariance is this expression, as I showed you earlier. And intuitively, to preserve the cross-covariance, we need two things. First, we want to sort of capture the cross-covariance within each latent class to ensure that the modalities are aligned for the full data. And second, we want to preserve latent class centers in both modalities. I'll explain both of these terms a little bit more in detail, but hopefully you can start to see how this is similar to the contrastive learning case. We have this like two-part objective, one part preserving diversity of the data, and one part preserving the centrality of the examples we select. So again, I'm going to introduce a similarity notion to help me kind of work through this. Here we call this cross-modal similarity, and cross-modal similarity measures how correlated the caption of image 1 is with the image, the caption of pair 1 is to the image of pair 2, and also how correlated the image of pair 1 is to the caption of pair 2. So here we say this has high cross-modal similarity because you can kind of see from the image and captions here that these are very, very correlated. But on the other hand, we have this caption, which is like a proper noun, and so it's unlikely to be highly correlated with a stock photo of a beagle. And we also have this sort of non-canonical image of a beagle, and that's unlikely to be strongly correlated with the caption, a stock photo of a beagle. So that's high cross-modal similarity and low cross-modal similarity. So now, similar to the previous case, like we kind of have to find a way to approximate this like tractably. And we can use the intuition that a vision and language encoder that are trained with the clip loss are automatically going to ensure that you have high cosine similarity for representations of correlated captions and images. So we can then use the representations of some proxy model, FP, FL, to approximate this cross-modal similarity. And then we kind of define what our approximate notion of cross-modal similarity is, and we're just going to refer to this as cross-modal similarity. And it's essentially the sum of cosine similarities between the representation of caption 1, image 2, and image 1, caption 2. So now, to preserve the cross-covariance of the data, I said earlier we want to do these two things, and the first was alignment of the modalities. We want to preserve the cross-covariance within each latent class. So what I mean by that is that we essentially want to pick examples that are in these highly correlated areas. Like we want to capture, like that's the bulk of the cross-covariance within latent class, these super dense areas, and we want to pick examples from those areas. And this is the formal objective we use to find that. The intuition behind this is that a good proxy model will result in high cosine similarity for these most central examples in different subgroups. So essentially what we're doing here is we're measuring the cross-modal similarity of an example to itself. So it's the cosine similarity of the image representation and the caption representation of a pair itself. And by picking the examples that are highest in this sort of value, we're going to be picking the examples that are in the most correlated areas. And you can think of these as the most central examples in different subgroups within a latent class. So visually, that kind of looks like this. And this particular part of our objective is also known as the clip score. This is a baseline we use later in our experiments. So the second part of preserving cross-covariance is preserving latent class centers in both modalities simultaneously. So the only difference from the single modality case here is that because you have to pick image caption pairs, you can't just optimize for preserving latent class centers in image space and caption space separately. You need to do this in a joint fashion so that the image caption pairs you pick are central in both modalities. And the way we do this is by picking examples that are cross-modally similar. So picking examples being the subset SK that are cross-modally similar to all other examples in that latent class. And so what that looks like, And so what that looks like is this. You have some image you pick, and this image is cross-modally, is very similar to a bunch of captions. And the corresponding caption is also similar to a bunch of images. And that's why this image caption pair is something that satisfies this part of our objective. So putting things together, we want to preserve the cross-covariance of each latent class to ensure alignment, and that's the diversity part of our objective. We want to preserve latent class centers in both modalities simultaneously, and that's the centrality part of our objective. And we have this objective that's just a sum of those two sub-objectives we defined. That is our final objective for what subsets are good. And again, this is a set function. In this case, it's a non-monotone submodular function. But again, because it's submodular, we can efficiently find this from large data sets. And in our paper, we have like a formal guarantee showing that this method, which is called clip-cove, because it preserves the cross-covariance, it ensures similar cross-covariance and hence ensures similar training dynamics to training on the full data. So again, you can kind of see how this ensures that you have like similar gradient to training on the full data. So one part I left out here is like, we again assumed access to latent classes, but of course we don't have this. But in this case, it's actually even easier to get these approximate latent classes. We can take whatever proxy model we have and some arbitrary set of fine-grained labels, like for example, ImageNet, and then we can do zero-shot classification on our data set and partition it into latent classes using the results of the zero-shot classification. And so now I have some results for this. Here, the purple line is our method. The yellow line is half of our method, like clip score, the first part of our objective. And the blue line represents subsets that are selected randomly. And you can kind of see, and the black line on top is the performance of the full data. And you can see that for different tasks, which is like ImageNet distribution shift, and a bunch of other tasks, you can discard up to 50% of the data. Also, we then scale this up to like larger data sets, so conceptual captions 12 million. And we show that for subsets of size 5% and 10%, we can outperform the next best baseline by over 2 times. Sorry. There are also many heuristics we have. So clip score is one simple heuristic, and that's just like looking at the similarity between image and caption representations. We explained earlier why this is a good idea and why it works so well. It ensures alignment and hence preserves the diversity in your subsets. Another baseline we have here is called SEMD-DO. And the idea here is that because these image caption datasets are sourced from the internet, they often have many duplicate images. So can we deduplicate them for efficiency? And what they do is they cluster images and then discard images that are very, very similar based on their representations. And the third baseline we have is called CRHO. And this sort of the key idea here is that you want to select examples that are learnable but not easily learned. And the way they do it is that you have some partially trained model, which let's call the training model, and you have a longer fully trained model, or like just a longer trained model, which we'll call the validation model. And the score for every point is like how similar the image caption pair is under the validation model and under the training model. And so essentially, if you have that under the validation model, this image caption pair is very similar, you'll have high clip score there, which means it is learnable. But if it's not easily learned, then the clip score train, which is the clip score of a partially trained model, will be low. So those are sort of the points you want to prioritize. And this is very similar to the idea we discussed earlier in the dataset cartography paper, where you want to pick points of like middling difficulty. So this is another heuristic we have. But we find, this is the same graph we had earlier, but I've now added the heuristics. The green and red lines are CRHO and SEMD-DO respectively. But we find that like on a clean data set, on a relatively clean data set like conceptual captions 3 million, these kind of heuristics can't give us any further data efficiency over random subsets. And so you kind of are forced to go for like a more theoretically principled approach like clip-cove. And yeah, the full paper is here and it appeared in AI Stats. So I'll now hand over to Baharan for the last part of our talk.
Okay, I talk 15 minutes about LLMs that many of us are excited about, and then we wrap up and happy to take questions. Okay, let's talk about LLMs a little bit. Like, we know that I showed some plots in the beginning that LLMs benefit a lot, probably more than any other models, from better data curation and more data efficiency. So how can we think about kind of selecting subsets, that high-quality subset for training LLMs? So let's start by fine-tuning. Think a little bit about fine-tuning. Usually we have a data set, we have a pre-trained model, and we have a fine-tuning data set that consists of pairs of prompts and responses. For example, in supervised fine-tuning, we have questions, answers, and our loss looks like this log likelihood function that, given a question, we want to generate or predict the answer correctly. So we have a log likelihood on the right, and we minimize the negative log likelihood like many other loss functions that we do. Okay, and the question is that, can we find a small subset that closely captures dynamics of training on the full data, or fine-tuning, in this case, on the full data? So because we have talked about capturing the gradient all the way, let's think of whether we can capture the gradients for LLM, whether we can find a subset that closely captures the gradient of the full data. And this is very, very difficult. You can guess that LLMs are huge, like billions of parameters, trillions of parameters, very large. So even if we look at the last layer, which we looked at for the vision models, this is going to still be very huge, like the dimensionality of the last layer gradient. For example, consider Phi2, which is a model with 2.7 billion parameters, not very large these days. The last layer, if we look at all the parameters, it has 6.5 million parameters, very, very high dimensional. Even if we train with LoRa, right, which is kind of training the model, fine-tuning the model in a lower dimensional space, still this last layer, and I'm only talking about the V projection in the last layer, we have KQV. So still we have 300K dimensions. And you remember that we want to do clustering, and capturing the pairwise similarities in such high dimensional space becomes really meaningless, right? Like all the pairwise similarities become very similar, and we cannot find a meaningful subset. Okay. So there are two ways. I want to talk about two preliminary results, technically, that we have for this. The first one is kind of similar to the approach that Sid talked about for contrastive learning and for CLIP. Like, can we find something else such that implicitly we match the gradients, right? And the second approach that I want to talk about is explicitly, kind of lowering the dimensionality of the gradients and matching the low dimensional gradient. Okay, for the first approach, so there is this important observation that usually during the fine-tuning, the model changes to the small extent. Like pre-training changes the model a lot, but fine-tuning usually changes the model minimally. And we actually do not want to change the pre-trained model too much, because otherwise we harm the performance. So this is a good thing. So, but the changes are minimal and smooth. The loss is going to be more smooth during fine-tuning. And in particular, importantly, curvature is going to be small, much smaller than pre-training during the fine-tuning. So what we can show, and this is, again, preliminary, and the results that we have is that, assume two examples, that we are looking at the loss of these two examples during fine-tuning. And fine-tuning is usually a few epochs, not very long. So if these two examples have similar loss values, or loss trajectories, I would say, like let's put together all these loss values to get the loss trajectories. If two examples have similar loss trajectories during fine-tuning, and this trajectory is not long, right, because fine-tuning is short, then we can show that these two examples have very similar gradients during fine-tuning as well. And with this intuition, we can do the following. We can fine-tune a smaller proxy model, much smaller model, And we can capture or save the loss trajectories for all the examples using this much smaller proxy model that is fast to train. Now, we can cluster these loss trajectories, and based on the results that I showed in the previous slide, we know that all the examples in a loss trajectory cluster have very similar gradients during the training, right? And these are kind of very similar examples in terms of the effect that they have on the model during fine-tuning. So now, we can just sample from different loss trajectory clusters, and this is going to be our final subset. Now we can train the larger target model on this smaller subset, sampled that we took from different loss trajectory clusters, and we can have the theoretical guarantee that because we are implicitly matching the gradient of the full data during fine-tuning, then our model is going to have a similar performance to fine-tuning on the full data. There is a slight thing that is useful to pay attention to. So if we sample examples proportional to the size of these clusters, then we match the full data. But if we want to reduce redundancies and do kind of a balancing, we can sample equally from different loss trajectory clusters. And we observe that in the case of LLMs, this seems to be actually very useful to balance different groups of data. So let's look quickly at some experiments. We call this method S2L, small to large. This is on arXiv, not published yet. So the left plot shows the in-domain, like we are, in this case, we are training PyTia for 110 million on MathInstruct dataset. And the evaluation is a bunch of in-domain evaluation dataset and out-of-domain evaluation dataset, different types of math questions. So left plot shows the in-domain average accuracy, and right plot shows the in and out-of-domain average accuracy. X-axis is the data size, percentage of the data that we selected with our model, and different existing heuristics. And the black dashed line is fine-tuning on the full data, the accuracy of that. So you see that by only our proxy model is PyTia 70 million. We are selecting data with that to train the larger PyTia 410 million. Only by selecting 11% of the data, meaning 30K example, we can already outperform fine-tuning on the full data. And now, if we keep selecting more, and there is a large gap early in like for the small subset size between this method and the rest of the existing heuristical method. But if we do if we select larger subsets, now, both for in-domain and out-of-domain, we can do much better than fine-tuning on the full fine-tuning data, which is really nice, right? So notice that as we increase the size of the data, the baselines also do better. So they cannot do well in the small data regime. They do much better in the larger data regime. But the good news is that we are doing much better than training on the full data, which is really nice. OK. So another experiment, let's go a little bit larger. Can we fine-tune larger models too? And in this case, we are considering Phi2, which is 2.7 billion parameters, and Phi3 mini, which is 3.8 billion parameters. Our proxy is now going to be the PyTia 410 million. So here, we are selecting 50K subsets, small subsets, but we train on them the same number of iterations, mini batches, as that of training on the full data. This is usually the standard setting that people experimented, showed the results with forgetting scores and L2 and other methods. And you see that this is working pretty well, and even like matches the performance of full data with with 50K, much less than half of the data. And now let's look at training for the same number of epochs, meaning that much smaller number of iterations. So for example, 50% subsets, if fine-tuning is 3 epochs on the full data, I train for 3 epochs and 50%, like half of the time. And this is Phi3 mini now. And you can see that this is also performing very close to training on the full fine-tuning data now, which is nice. So for larger models, we need larger subsets, which is expected, but still, we can almost still reduce and drop half of the data and match or do better than fine-tuning on full data. Another experiment, fine-tuning Phi2 and mimicry. This is a clinical text summarization task, another domain, which is not math. And 50% subsets does much, much better than full data, and also 50% random subsets. These are different evaluation metrics for this data set. Okay. So last couple of slides, let's context switch and see if we can match the gradient directly, right? Okay, and get some guarantees for mini-batch SGD and getting a curriculum. Very similar idea to the one that I was discussing in the first part. Okay, this is our gradient matching objective function. And if you remember from the first part, we want to update the subset during the training, and this gives us a curriculum. And we want to find mini batches, small mini batches. We don't want to find one subset from the full data. Okay, issue, how can you match these very high dimensional gradients? So here, the idea was that can we go smaller? Can we reduce the dimensionality of these gradients and get something lower dimensional that allows finding a high-quality subset? So what we tried and gave us relatively promising results so far is that, as I said, there is this, as you know, there is this KQV matrices in the transformers. So in our experiments, we took the V projection, and it seems to be working than the rest of the matrices in the last layer. So we take the V projection, and even if we are fine-tuning with LoRa or other memory-efficient methods, this is going to be the same, like we just have a smaller V projection matrix. Now, we can get the gradient of this last V projection matrix, which, if you remember, is still very large to use, but let's have this for now. And imagine that we do not have a lot of memory. The good thing is that we can calculate this last layer V projection matrix gradient in a very memory-efficient way using ideas from zeroth order optimization. How can we do this? So in general, this is the zeroth order optimization formulation when we want to calculate the gradient. So we perturb the parameters 2 times, a little bit. We calculate the difference between the loss of these perturbed parameters, and then we divide by the amount of perturbation, and then we can estimate the gradients in just one forward pass. If you check the Meso paper, this is explained very well there, and this can be calculated efficiently with very minimum amount of memory, like inference amount of memory. So for us, we are only interested in the V projection matrix. So what we did is that we only perturbed the parameters of this V projection matrix by a little bit. And this way, we can calculate directly, very efficiently with one forward pass. We can estimate the gradient of the V projection matrix. So we do one forward pass. We can calculate this zeroth order gradient quickly. Now, this is still very high dimensional. We want to go lower. So what we did is that we used ideas from neural network pruning. So we said that, okay, let's sparsify this V projection. And we only considered the dimensions which has the largest gradient magnitude. How many? Like 1K or 2K, right? As small as that. Okay, now we can find a subset that matches this lower dimensional, much lower dimensional gradient estimates that we find this way. And the algorithm is similar to what I explained in the first part. So we take a random subset, larger random subset, and we find a smaller mini batch that matches this lower dimensional gradient estimate in the previous slide. So here our larger subset, this is preliminary results. And we are going to put this on archive such that you can check the details very soon. But our larger subset, a larger mini batch or random subset, is the size of 128, and we want to select 64 out of 128. We can do larger. We can go to 56 or potentially larger. And so as you see, this is, again, fine-tuning phi2 on the math instruct dataset. And you see that if we are training for 1,000 mini batches, we can already match the performance of training with large mini batch. That's why we called it memory efficient training, because we are simulating, if you remember, training with large mini batches that requires a lot of memory. So now let's train more. Let's train for 2K. If we train for 2K, you can see that we are still with this gradient matching idea. We can match or even do a little bit better than training with large mini batch, which is nice. And here we are already getting the full fine-tuning performance, and we are doing good. Okay, so this can be potentially also applied to pre-training, right? It's just that it requires very good GPUs. Okay, so let me also mention briefly existing heuristics that do exist for data selection for LLMs, and we can connect what are the ideas to previous sections. So for pre-training, people have tried selecting based on perplexity, L2 score that I explained, and memorization ranking. Memorization ranking says that for a given question, like the generated answer, let's see if this example exists in the training data, how many of the generated keywords exactly match the data that exists in the training data. So that is memorization ranking, and people figured out the examples with middle perplexity work best. For pre-training, this is very similar to the dataset cartography, that examples that are having medium amount of variation in their predictions are not easy and not noisy, and they work best. So this is for generative models now. The duplication, very similar to SEM-dedupe, that Sid explained for clip models. People applied here too. And these are for pre-training. For fine-tuning, most of what is explored so far is manual data curation, which kind of confirms the importance of high-quality data for LLMs. It is very useful, but it's super expensive, and it's not something that we can really do very often. Then another approach that is explored a lot, is used a lot, is using another LLM to select data for training a target LLM. For example, GPT or ChatGPT are explored a lot, and people play with the prompt to kind of find high-quality data to train another language model. And selecting centroids of the hidden state or kind of representations is also explored using a pre-trained model. And I showed some of these baselines in the first fine-tuning results. Okay, there is another line of work which I want to mention and say that this is a slightly different line of work, but another line of work assumes that we have a target task at hand, and then we can select directly some of the training data that directly maximizes the performance on this target task, right? The objective is slightly different. The objective is maximizing the performance on the target task, which is different than the previous approaches. And here, people have proposed using influence functions and using data models. Both, I believe, are being presented in ICML this year, and a couple of other approaches also exist. Okay, future directions. And wrapping up. So first, there is a very interesting direction that we have been exploring recently, and I found it really interesting, is that a lot of times, not a lot of times, so we figured out, even if you are training in a simple supervised model, changing the distribution of the training data can improve your in-distribution performance. This is very interesting and have not been explored before, so I think this is a very good direction to explore in the future. So it seems that because gradient methods have simplicity bias, have a bias towards finding simpler solutions. And in over-parameterized models, there are multiple solutions that can have a similar generalization performance. So if we can reduce this simplicity bias during the training, we can kind of push the model to find a more generalizable solution. So this is a very nice problem, I think, and you can check this archive paper to see more. Another one is that can we directly generate high-quality data? So far, we have talked about selecting a high-quality subset of a big data. Can we directly generate high-quality data? This is not dataset distillation, right? Dataset distillation matches the training gradients, generate data by matching the training dynamics, for example, based on gradients. But here I mean, like, can we just directly generate the real-looking data, not distilled data, and do better than subset selection, which I think is doable and is a very interesting direction. Can we find subsets that guarantee the performance for other optimizers? For example, for LLMs, we usually train with Adam, and so far guarantees are for SGD only. So this might be nice to explore as well. And obviously, improving the existing methods. A lot of the methods like self-supervised learning, CLIP, and LLMs, there is a lot of room to improve these solutions, and I'm hoping that many of us keep working on these methods and improve these methods further. Thank you so much. And we are going to upload the slides in our website.
Okay, so thanks. Because of the lack of time, so I think we conclude the tutorial here. So thank you, the speaker again.